All right. First thing I want to do today is do a proof. Okay, I said there could be a proof on the exam, or maybe even two. I have put them on old first exams. In one of the lectures, I do a proof of a property of logarithms. One of the properties, the fact that the log of a product is the sum of the logs. Here today in class, let's do another proof of a logarithm property. And let's just go ahead and do it for the natural logarithm. I could do it for log of any base, but since we use the natural logarithm the most, we might as well do it for the natural logarithm. That the natural log of some number, call it a, to an arbitrary power p is p times the natural log of a. A does have to be positive here, because you don't want to take a natural log of a negative number or 0. P can be any real number. P is any real number. Okay, so like I said, in one of the lectures, I do a proof like this, a proof that the log of a product, the log of a times b, is the sum of the logs, log of a plus log of b. This is another property of logarithms that we want to be able to prove. There are appropriate times in a calculus class to be able to work at proving something, and I think this is one of them. This should be able to prove in a pre-calculus class as well. There's no calculus really involved. So what do you do? How in the world do you show these things are equal? Well, the first thing you should realize is that you just have an equality between numbers here. Think of a and p as fixed. Log of a to the p power is just some number. P is some number and log of a is some number. You could give those numbers names if you like. It might be helpful. It's kind of arbitrary. You could call this one maybe b, and this one c. You already have a p in there, and you already have an a in there, so I might as well use new letters. So the goal is to show that b equals p times c. If I let b equal the natural log of a to the p and c equal the natural log of a. That's your goal. All right, that's a part of the battle. Maybe 10, 20% of the battle is to figure out what you want to show. The vast majority of the battle is figuring out how you get there. How do you show this? And it's not real clear. All right, one key thing is you always end up using properties of exponents when you try to prove properties of logs. So you're assuming something. You're assuming you know properties of exponents. You're assuming, for example, this is just a side calculation, not part of the proof. You know that, let me use x's and y's here, and maybe a z. X to the y power to the z power is x to the y times z. That's a property of exponents that you know that you multiply those exponents. This little thing here is supposed to be a z. Mathematicians tend to put little lines through their z's because that's supposed to be a 2, and this is supposed to be a z, okay? So we put little lines. This says x to the y power raised to the z power equals x to the y times z power. In that kind of situation, you multiply the exponents. That's an example of a property of exponents that you can assume is true. And in fact, it's exactly the property that we need with this particular one. How? That's the next question. With properties of logarithms, use the definition of what logarithms mean. What does it mean for b to be the natural log of a to the p power? What does it mean for c to be the natural log of a? Well, it is log base e. That's natural log. So you got to bring the number e into play in some way. Take the simpler one. What does it mean that c equals natural log of a? How can you state that equation in terms of the number e? Anybody know? E to the c equals a. Yeah, logarithms, in effect, can be thought of as exponents. That's the way that people commonly describe them. Well, that's a little bit vague. It means if you make this the exponent of the number e, this number here, you'll get a. That's what it means. You could write since c equals natural log of a, e to the c power, or if you prefer, e to the natural log of a power is a. You know that. You've seen that kind of equation before. right? That's using the definition of the logarithm because it's really using the definition of the natural log of x, say, as the inverse function of e to the x. E to the natural log of a, it's kind of like the e and the natural log cancel out as inverse functions, and you're left with a. And since b equals natural log of a to the p, e to the b, or e to the natural log of a to the p, equals what? Same kind of argument here. This equals. You want to go ahead and say the person who had their hand raised over here before? I don't remember your name. She doesn't see me. Do you want to say here what this equals? For this line right here, e to the natural log of a to the p.
I'm not sure. Sorry, I was writing.
Okay, sorry.
When did you e to the?
It would be just a to the p.
Oh yeah, because ln.
Yep, the e and the natural log kind of cancel out in a sense as inverse functions. You're left with whatever's inside the parentheses there, a to the p in this case. Okay, that's another 20, 30% of the battle. We're left with 40 or 50% left. I said you want to use this. I'm trying to think about also what you're trying to show. I'm trying to show b equals p times c. And here I'm saying e to the b equals a to the p. Think about this here. If you could show e to this power also equals a times p, wouldn't that do it? Get what I'm saying? I know e to the b equals a times a to the p. I'm trying to show b is p times c. If I replace the b with p times c and got the same thing, wouldn't that show that b equals p times c? The answer is yes, it does. So it's good to give a little extra reason. But does that even work? Let's say it this way. By a property of exponents, in fact, this property is what we're about to use here. E is going to play the role of x. P times c is playing the role of y times z. I'm going to use this property from right to left here. And what do you think I want to do with this? I do want to use this property from right to left, but it is a little tricky. Should P be y and C be z, or should it be the other way around? What would be better if I want to get this answer out? I want to show this equals a to the p. Using this fact, perhaps, or this fact, perhaps. Do you see it? Anybody? You want to use the C for Y, actually. Is that what you said, or did you say P? Okay. Use the C for Y because if you do, it'll look like this. And then you can use what you know. You can substitute. E to the C equals A. Therefore, you can replace that E to the C with A. Hey, cool. You're left with A to the P. I did what I wanted to do. I wanted to show this was equal to A to the P, equal to the same thing there. Are we done? Essentially, 3 dots means therefore, if you want to use a shorthand, therefore, E to the B is A to the P, but that's also E to the P times C. Our goal is to show B equals P times C. This looks like we should be able to do it, doesn't it? I mean, can we cancel the E? These are the same thing up here. Can we kind of cancel the E? Well, don't call it cancellation. It's not really cancellation. You can get rid of the E. You can say this means B equals P times C like we wanted to show. But it's not because you're canceling the E. It's because the function e to the x is a one-to-one function. Since e to the x is a one-to-one function. Remember one-to-one? Talked about that a couple weeks ago now. Think of e to the x as a function, defining a function of x. You've got e to some power equaling e to some other power, perhaps. Could the powers possibly be different? Could the inputs be different? No, because the function's one-to-one. It passes the horizontal line test. There's the graph of e to the x. Every horizontal line goes through it at most once. So for every output, there's at most one input. Here I've got the outputs being the same. The inputs must be the same too. B must be P times C. And that means we're done. We did what we wanted to show. Many mathematicians start talking in Latin when they're done with a proof. They write QED stands for quad erat demonstrandum. But as a Christian mathematician, I like putting PTL for praise the Lord. We're done. Okay. Now you look at that kind of thing, and you're like, oh boy, symbolic abstract math. I kind of followed it when he did it, but now I look at that and I have no idea what the hell that means. That means it takes work. You got to spend time thinking about it. Okay, you got to spend time re-going through this argument. Also watch that part of that lecture about the log of a sum being the sum of the logs. There's another property, the log of the log of a product being the sum of the logs. There's another property that the log of a quotient is the difference of the logs. Like that, you should be able to prove as well. And these are key properties, okay? Why should you learn this kind of thing? Isn't it good just for math majors? It's good for everybody. It's good for everybody to gain some skill with logical thinking. For one thing, to defend your faith. For another thing, it could be useful on the job. You could have an employer, your boss, well, maybe they're thinking about firing you and you want to justify them not firing you. You can give logical reasons why you are beneficial to the company, or maybe it's not such a dreadful situation, you're not going to be fired, but you want to convince your boss to spend money to buy some equipment that you need or something. Developing logical reasoning skills is helpful for that kind of thing. Okay, it is good for everybody, not just math majors. Of course, we are thinking about math here, so we're applying logical reasoning in the context of math. But that kind of practice helps you become a better logical thinker. Precise thinker might be another way to say it. You've got to be able to deal with things symbolically, abstractly, reason abstractly. It's all important. If you think, oh, I don't care about a career. Well, you might have a kid someday and you want to help your kid develop logical thinking skills. There's another application, okay? So it's worth doing. All right, our main topic for today, though, is more about limits. And to motivate the topic of limits, let's put it in the context of chapter 2, start talking about derivatives. Let's say your distance traveled, often called S, which makes you think it's a speed, but no, S is actually more commonly a letter used for distance traveled, or position, which are not quite equivalent, but let's pretend this is a distance traveled. Distance traveled in meters, say, as a function of time, t, in seconds. So this is a physics application, is going to be some function of t. What function of t am I going to pick? Well, I'm not thinking about any particular given situation. I'm not thinking about a rock falling through the atmosphere under the influence of gravity and air resistance and that kind of thing. Those are very important kinds of models, but that's not what I'm thinking about. I'm just pretending for some reason, this function is the function t cubed. Okay, maybe you're in a car and somehow you're hitting the accelerator in such a way that your distance traveled as a function of time is t cubed. The graph of this, you'd want a graph for t greater than or equal to 0, looks about like this. Looks like it's a piece of a parabola. It's technically not. Cubics do not have graphs that are parabolas. Parabolas are very specialized kinds of curves. And there are plenty of curves that look like they're pieces of parabolas that are technically not. But it's not a real big deal to worry about. At time 1, you've actually traveled 1 meter. F of 1 is 1 cubed is 1 meter. At time 2, after 2 seconds, you've gone 8 meters. After 3 seconds, you've gone 27 meters. After 4 seconds, you've gone 64 meters. You're going pretty slow at first, but you're obviously speeding up. How can you tell just from the graph that you're speeding up? Is it the fact that it's increasing or the fact that it's concave up? Telling you that you're speeding up. It's the fact that it's concave up, yeah. The fact that it's increasing means you're moving. You're traveling, the speed is positive. The fact that it's concave up means the speed itself is getting higher and higher. Your speedometer is going higher and higher. You are speeding up. You are accelerating. Question 1. What is the average speed from t equals 1 to t equals, oh, let's say 4? Common letter, use the letter V for speed. V can also mean velocity. Technically, speed and velocity are different things, though they're often the same. Technically, the speed is the absolute value of the velocity. Velocities can be negative because velocity takes direction into account. But we're only moving in one direction here. So speed and velocity are equivalent. You might call it V sub average for an average speed. What's the average speed? What's a formula from physics for the average speed? Something divided by something else is what I'm hinting at here. Distance divided by time. Another way to look at this equation is to multiply both sides by time and say distance equals speed times time or rate times time, rate being the speed. So that only gives you, that equation only works if you got either a constant speed or you're using the average speed. Because the speed is changing here, it's not constant. The distance is just the distance at the end minus the distance at the beginning. 64 minus 1. In function notation, that's f of 4 minus f of 1. That's the distance traveled. And the time elapsed is, well, 4 minus 1. And this is in meters and this is in seconds. So the answer is a rate in meters per second. F of 4 is 64, f of 1 is 1. You get 63 divided by 3, that'll be 21 meters per second. That is your average speed from time 1 to time 4. It's important to be able to interpret this geometrically. Let me draw a bigger picture here. Let's say time 4 is right here. Time 1 is right here. There's 1 up here is 64. This is not a perfect graph. Just trying to get the idea here. Distance divided by time is really a change in S divided by a change in T. This is a delta S divided by a delta T. It's really a rise over run, a slope of some line. Do you think you could draw what line this is the slope of? Here's a big hint. Draw a line connecting the points, the straight line. It's supposed to be straight. Pretend it's straight. It's called a secant line. A secant line to a circle is just a line going through 2 points on the circle. And a tangent line to a circle goes through 1 point. For general graphs that are not necessarily circles, graphs of functions, a secant line is just a straight line between 2 points on the graph. That's all it is. That could intersect the graph somewhere else, because the line could keep going up here, and theoretically the graph could go like that, though it doesn't. They could intersect again. And a tangent line at a point is doesn't necessarily touch the curve at just 1 point, but like we talked about a week ago or so, it's what the curve looks more and more like as you zoom in closer and closer to the given point. But that secant line has a slope, rise over run, equal to the average speed, 21 meters per second. You should include units. This is T in seconds. This is S in meters. A slope is a rise over run, a change in S divided by change in time. Something in meters per second is the way to think of it. The actual motion from time 1 to time 4 is not a constant speed. It's a changing speed, starting out kind of slow, but then the graph gets steeper and steeper, that by the end you're going pretty fast. Faster than 21 meters per second, in fact, at the end. The fact that the average speed is 21 meters per second means if there was another car, say, traveling from time 1 to time 4 and going from position 1 meter to position 64 meters, the graph of their distance as a function of time would be straight if they're going at a constant speed, and they would start and end at the same spot. The car that was going slower at first eventually catches up because by the end it's going faster. You need to be able to, in your mind, imagine such things. That's essential for both doing well in this class and applying calculus well in other classes, is that you can imagine that kind of thing. You can imagine what the graphs are telling you in that way. It's really, really important. You might even say perhaps the most important skill you can get out of a math class like this is being able to interpret graphs and what they tell you about the real life situation they're modeling. In this case, motion. All right, well, that's from time 1 to time 4. I could also do from time 1 to time 2. From time t equals 1 to time t equals 2, I could find the average speed as well. The average in that case, delta S over delta t, is f of 2 minus f of 1 divided by 2 minus 1. The starting time is still 1, but the ending time is now 2 instead of 4. You should be able to predict what's going to happen before doing the calculation by looking at the picture. Not to get the exact answer, but you should see, hey, this is going to compute the slope of this secant line. I can see that that slope is smaller. I should get a smaller answer. F of 2 is 8. You get 7 over 1. You get 7 meters per second. That is the slope of this line. definitely smaller. How about an even smaller time interval from t equals 1 to t equals, oh, how about even 1.001? 1,000th of a second, right? You can't even, if you're doing a stopwatch kind of thing, you can't go that fast. That's how, that goes by so fast. You can't even really do 100th. That even goes by too fast for most people on a stopwatch. But we can still figure out this average speed. Change in S over change in time, but now the change in S is f of 1.001 minus f of 1, that's the change in position, divided by the change in time, 1.001 minus 1. All right, I'm going to use my calculator. 1.001 cubed, the function is t cubed. 1.003003001. That's probably actually exact. It's probably not a repeating decimal. Minus 1 over 0.001. Subtract 1 from this, divide by 0.001, and you get a number close to 3. Approximately 3.003, now I'll round, meters per second. And I could keep going further. Let me just do it on the calculator, in fact. Let's go from time 1 to time 1 point. Let's make it, say, 6 zeros and then a 1. 1.1, 2, 3, 4, 5, 6 zeros and then a 1 cubed minus 1 is my change in position. My time elapsed would be 0.000001. Oops, I forgot a 0. Three. Really? Exactly 3? Actually, that's rounding. The calculator is rounding. It's not exactly 3, but it's so close that it's saying, well, it's effectively 3. What are we observing here? We're observing the concept of a limit. The limit of the average velocities as delta t goes to 0 seems to be equal to 3 meters per second. And that indeed is true. And that is the slope, not of a secant line here at this point, but a tangent line to this point. This other one in purple, this was a secant line. This green one is a tangent line. Its slope is exactly, and this is exactly 3 meters per second. What that's telling you is if your speedometer was super duper accurate, giving you your speed at every moment in time, essentially accurate to a lot of decimal places, at time 1, you would say 3 meters per second if it was given in meters per second. Speed at a moment in time. Instantaneous speed is what this is often called. Now, people who've taken physics are kind of used to this thing, right? You're used to instantaneous speed or instantaneous velocity. People who haven't taken physics are not so used to this kind of thing. This is a big part of what calculus is about. But where is the calculus here? Have I done calculus? Well, I laid the groundwork for some calculus to verify that the speed truly is 3 meters per second. If your position is, your distance traveled truly is t cubed, we need to do a limit calculation, section 1.8. And when we do that limit calculation, we are essentially finding something called the derivative of this function at time 1, and we write f prime of 1. The derivative of the function f evaluated at t equals 1 That's not the only notation for this. You can also, since the dependent variable is s and the independent variable is t, you can emphasize it's a rate of change by writing ds dt, vertical line, evaluate at t equals 1. This ds dt is, well, it kind of looks similar to delta s over delta t, doesn't it? Delta is the Greek version of d. Hey, it's described as delta, which starts with d. That's great. That's a fraction. Delta s divided by delta t is an actual ratio, a fraction. ds dt technically is not a fraction, even though it looks like one, doesn't it? However, even though it's technically not a fraction, it often doesn't hurt to pretend it's a fraction. And I'm being completely serious here in what I'm about to tell you. And this is yet another one of the most important things to get out of calculus. Calculus is full of things where, well, I call them convenient fictions. We pretend, in this case, this is a fraction, even though it's really not, is an example, a prominent example. It's not a fraction, it's really a limit of fractions. It's a limit, LIM, as delta t goes to 0, so you write delta t arrow 0, of f of 1 plus delta t minus f of 1 divided by delta t. Delta t, delta s, those are single quantities. It's not delta times s, it's not delta times t. It's delta s and delta t. And you could think of this expression on the top as being a delta s, if you like, but I'm just going ahead and using the function name right away. It's a limit of fractions. It's technically not a fraction by itself. You're not going to divide two things to figure out what this is. You're going to divide things and then take a limit, if the limit exists. Oftentimes, including in our calculus book, you'll see the letter h used here instead of delta t. And that's fine. Doesn't matter what letter you use. I'm going to go ahead and use a delta t here still, just for the sake of emphasizing it. But in the book, you'll see it switched to an h, another common letter to use. Well, how do I do this? You carry the limit sign along for the ride and only use it, so to speak, at the very end. You only take the limit at the very end. Just like when we were doing the example from last Friday with finding the horizontal asymptote. I think it was last Friday. By doing a limit calculation, and we used the properties of limits, we had a fraction, we brought the limit up into the fraction. We had the limit of a sum, we broke it into two limits. You remember doing that? It was a real long, not pleasant thing. It's not pleasant for me, to tell you the truth, either, because I like to save as much writing as I can. Otherwise my arm gets too tired. I don't know, maybe I need to do more push-ups or something, but that's what we were doing, is we were using properties of limits. Are we going to use properties of limits here? Not in the same way as we did last Friday. Though we will use a property of limits related to continuity here at the end. So what do? I've got to use the formula for the function. It was t cubed, remember? F of t was t cubed. I've got to use that formula. So I need to replace f of 1 plus delta t with 1 plus delta t quantity cubed. No matter what's inside the parentheses, no matter how crazy it looks, that's what goes in place of, in this case, t. Or if the function depends on x, that would go in place of x. So I need to take this entire quantity, 1 plus delta t, and cube it. And again, delta t just represents a single number. It's not delta times t, it's just delta t, a number. F of 1 is just 1 cubed. Delta t is, well, whatever it is. In effect, in this limit calculation, delta t is the variable. That doesn't look so easy to figure out, does it? You can't plug in delta t equals 0 because you'd be dividing by 0. Can't do it. Or can you? Does anybody know a way to actually solve for this? Have you taken calculus before? Probably some of you have. You remember doing these kinds of problems? Nobody? It's okay if you get it wrong. I'm not going to get mad. Other people won't get mad either. It's okay to be wrong. You should try to be right. You want to say? Go ahead. That is something we're ultimately going to do. So you're right on track. That ultimately we're going to factor a delta t out of the top actually and cancel it with the one on the bottom. But we can't quite get there yet without doing some other stuff first. All I'm looking for is the word simplify. Simplify. Expand that cube out. Wait a minute. A cube of binomial? Can we do that? Yeah. There's a couple ways you can do it. You could square it first and then multiply it times another factor of 1 plus delta t. Or if you know Pascal's triangle, which you probably learned at some point in the past, there's something called the Binomial Theorem that allows you to figure out what the sum of two things to a power is without having to do a bunch of work. And with cubing, you use this row of Pascal's triangle to figure out the coefficients. You've done this before? Most of you should have in high school. Let me go ahead and just write what you would get. By the way, the way you figure out this triangle is you make ones along the diagonals, and then in the main part of the triangle, the 2 there comes from 1 plus 1. The 3 here comes from 1 plus 2. The 3 here comes from 2 plus 1. The 4 here comes from 1 plus 3. The 6 from 3 plus 3. And the 4 from 3 plus 1. And you can keep going forever and ever. But what the binomial theorem says is that these numbers in this row will be the coefficients you get of cubing this thing. The first coefficient of 1, and the first thing you multiply it by is whatever this thing is cubed. It's 1 cubed, which is 1, but let's go ahead and write it anyway. Then you add on the next term, 3 times this first term squared times that thing to the first power. Then you go to the next term, 3 in the Pascal's triangle in this row, write it down times this thing to the first power times this thing squared. And finally, you write down the last number, 1 times the second thing cubed. And I'm running out of room. Don't forget about subtracting 1, and don't forget about dividing all of this by delta t. That can be figured out also by just actually doing the multiplication, foiling first to find 1 plus delta t squared, and then multiplying that by another 1 plus delta t and simplifying. You'll get the same answer if you don't make a mistake. If you have not made a mistake with problems like this, where the function is a polynomial or a power function, t cubed is both a power function and a polynomial, you will get cancellation of every term that does not involve delta t on the top. And then you'll be able to factor a delta t out of what's left. Each of those terms has a common factor of delta t that can be factored out. To give you this. Remember, delta t is one quantity. So when I write things like something like this, I mean delta t quantity squared. You can use parentheses if you like. Now you cancel these delta t's. Divide them out is probably a better word to use. The fraction becomes a 1. They don't become 0. They become 1. And you're left with this limit. And now if you plug in delta t equals 0, you're not dividing by 0. When you plug in delta t equals 0 to evaluate this limit, you get 3 plus 3 times 0 plus 0 squared is 3 plus 0 plus 0 is 3. The answer is 3 meters per second. Yay. Can I clarify anything there? I've not completely justified everything here. I'm about to talk about how to justify these steps. And you should be able to justify these steps for exam 1 in 1 week for this kind of problem. How do you justify these steps? Well, this is just notation at the top and terminology. There's nothing going on there but notation and terminology. The equality right here is because of the definition of what the derivative is. Def of derivative. That's what the derivative of this function is when t equals 1. Notice I am using the function f, so it's related to f, I should say. And I'm plugging a 1 in right there and right here. If I was finding f prime of 2 instead of f prime of 1, I'd plug a 2 in right there and right there. If I was finding f prime of 3, I'd plug in a 3 right here and right there. This is just, well, substitution using the formula for f. This is just simplification. Simplify. If you want, you can say we use the binomial theorem there, but I'm not expecting you to. This is more simplifying. And while you can say this one is simplifying, there's really a bit more going on with this equality right there, related to what we talked about last Friday, actually, with limits and holes in graphs. Look at these two expressions right here and right here. They are equal to each other for all values of delta t. Well, as long as delta t is not 0, at least. If I were to graph this function as a function of delta t, which sounds like a really weird thing to do, but certainly could be done, it would look like the graph of this function as a function of delta t, except there'd be a hole in the graph of this one at delta t equals 0, just like with those rational function examples from last Friday. In fact, this is a rational function of delta t. Its graph again looks like the graph of this one, which is quadratic. It looks like a quadratic function of delta t. It's going to look about like this. It's going to look like a parabola about like this. Technically speaking, there's a hole in the graph missing, a point missing for this function at delta t equals 0. But it's not a vertical asymptote, it's just a point missing. The limit still exists. And you can find the limit by finding the second coordinate of that hole, of that missing point. And it's got to be 3, about what we just calculated. Because this function equals 3 plus 0 squared is 3, excuse me, when delta t equals 0. The graph of this has the hole filled in. The discontinuity is removed. So graphs with holes in them are not just curiosities. They're actually essential to calculus. It's not a graph of the original function. This is not f of t equals t cubed here. It's the graph of this thing or this thing as a function of delta t. And I'm letting delta t go to 0. I'm letting it approach 0 from both the right and the left, in fact. It's a two-sided limit, you might say, and the limit does exist and it equals 3. All right, that's one big reason to talk about limits. It's not the only reason. Let's spend our last 20 minutes or 15 minutes focusing on limits now. Again, we've been talking about them intuitively with graphs and formulas and some calculations like we just did. Let's talk about them graphically a bit more. Well, and I should mention what, okay, I'm going to mention, in talking about what I'm about to talk about here, I am going to mention why this equality is true as well. Let me say that this one is, it's more than simplification. It's simplification plus the definition of a limit, which I haven't described yet, but I will describe it here. And this equality right here is really based on the notion of continuity. Continuity of this function 3 plus 3 times delta t plus delta t squared as a function of delta t at delta t equals 0. Now, it's technically continuous everywhere, no matter what delta t is, but the only thing we technically need is the continuity at delta t equals 0. And that'll be the first thing I emphasize here in a graphical approach to limits. If you've got a function that, say, looks like this, and it is a nice and continuous function, like I just drew, I can draw it without picking up my writing utensil. And I'm letting x approach some specific number c. The fact that this graph is continuous everywhere, including at c, means that the limiting value of this function, y equals f of x, say, where this is x and this is y, as x approaches c from either the left or the right, is the same, and in fact, it equals the function value. It equals f of c. The limit as x approaches c of f of x equals f of c, whatever that number happens to be. Let's pretend it's something specific. Let's pretend this is 2. This is really what it means to be continuous at c. Because if I draw another function, maybe up here, that maybe happens to not be continuous at c, y equals g of x, and maybe it is defined at c, but it's defined to be something else other than the second coordinate of this point. Maybe it's up here. Maybe the actual value of g of c, just to pick something specific, is, let's pretend it's 7. Whereas the limiting value of g as x approaches c is not 7, but maybe it's 5.5. That's the limit as x approaches c of g of x, but this is g of c itself, 7. Again, it seems like a silly thing to do. Why would you do that kind of thing? But theoretically, it's possible. And technically speaking, sometimes you have weird discontinuities like this in unexpected situations that have real life applications. There are situations like that. Not going to get into that at the moment, but the limit here as x approaches c of g of x equals 5.5, but that's not equals to 7, which is g of c. F is continuous at c, and g is not continuous at c. However, I can still talk about its limit. Its limit does equal 5.5. And by a property of limits, you should, on homework and exams, first exam here, be able to find a limit like this. Find the limit as x goes to c of, I don't know, 8 times f of x minus 3 times g of x. Assuming the limits of f and g exist, which they do. This is the limit of a difference. That is the limit, the difference of the limits, I should say. For extra emphasis, I'll use parentheses like this. The limit, watch where I'm pointing, the limit of a difference of two functions is the difference of the corresponding limits, assuming these limits all exist. If they don't exist, then this doesn't work, but assuming they exist, which they do in this picture. And then the constants can also be brought out in front. The limit of 8 times f of x is 8 times the limit of f of x as x approaches c. And the 3 can be pulled out in front here. And these are multiplications going on. 8 times this limit and 3 times this limit. And for extra emphasis, I'll put parentheses around these. Those are individual numbers. In fact, based on this graph, the limit as x approaches c of f of x is 2, and the limit as x approaches c of g of x is what, 5.5 or 7? This one, 5.5. So we get 16 minus 16.5. Didn't mean to make those so close, but it's okay. The answer is negative 0.5 for this limit. When I don't put a plus or a minus sign to the right of the c, I'm saying I'm letting x approach c from either side, either from the left or the right. It's called a two-sided limit. There are some functions where the one-sided limits exist, but not the two-sided limit. Just a generic graph again. Say you got a function that looks like this. My new f of x here, this is c. Let's pretend this number is 3.2, and let's pretend the second coordinate of that missing point is 5.8. The limit as x approaches c from the left, the negative sign there means from the left. It does not mean c is negative. I'm letting x approach c, get closer and closer to c without actually equaling c necessarily from the left through values of x that are slightly less than c. This exists and equals 3.2. The limit as x approaches c from the right, put a plus sign to the right of the c, excuse me, does not mean c is positive, though I've drawn it to be that way. Is it 5.8 or not? I mean, that point's missing. It's not a part of the graph. The point with coordinates c comma 5.8 is not part of the graph, is what I'm emphasizing by drawing a little circle there. Does this limit equal 5.8? It does, yes. In spite of the fact that f of c is 3.2. The overall, therefore, the overall two-sided limit as x approaches c does not exist. DNE stands for does not exist, because the one-sided limits are different. The one-sided limits from the left and right have to be the same in order for the two-sided limit to exist. By the way, you could say f is continuous at c from the left, but not from the right, because you got this equality here, but you do not, this does not equal that. But don't worry about it. We're not going to think about one-sided continuity in this class, other than me just mentioning it briefly right there. And by the way, the value of f of c being 3.2 is irrelevant for these limits. I could have made f of c be 4.5 or something. Or something else. The function would still be defined, but these limits would still be true. This one here and this one there. But this one would not equal f of c if, in that case. Can I clarify anything? This is not easy stuff, but something you should definitely know for exam 1 and give you more homework problems due on Wednesday for this. Go to Math Lab if you need to. Limits can fail to exist in wild ways. Have I shown you the graph of sine of 1 over x? Did I do that in here? Or I know I did it at least in one other class. You're saying yes, I did? I did. That's worth looking at again. The limit concept is definitely subtle. We'll do this as a piecewise function. By the way, to get this writing assistant palette to show up for you when you open Mathematica, you go up to palettes and go down to writing assistant. And I just clicked this button right here to get this to show up. Say it's sine of 1 over x when x is not 0. And I don't know, anything I want, 0 when x does equal 0. I think I emphasized when you're doing it in the way I'm showing you, you definitely need double equal signs here. A single equal sign will mess things up because it'll set x equal to 0 and you don't want that. To get the not equal to, I think it's in this palette somewhere, but I just did a shortcut, keyboard shortcut. I did escape exclamation point equals, then escape again, makes a not equal to. I didn't have to make it a piecewise definition, but oh, let's see. What am I doing? I want to look at the plot of this as x approaches 0. This graph oscillates infinitely many times on any little window near 0. And by moving the slider here, you can zoom in near 0 and it'll look like it's oscillating faster and faster. And yeah, that's not a proof that it oscillates infinitely many times, but it helps you believe it. And that is true. And this means the limit does not exist, but it does not exist in a weird way. However, here's my final thing to show you, but this is important. You might hope that you can always just think about limits in terms of either calculators or graphs, but your technology can be deceiving you. This graph, oh, that's not the one I want. I thought it was the one I wanted. Okay, this is the one I wanted. This graph looks like it has a limit as x goes to 0. But watch what happens when I zoom in. All of a sudden, what's going on there? Is it oscillating infinitely often? No, that's computer error. The graph actually doesn't look like that. It looks nicer like this. In fact, the limit does exist and it's 1/6. But it's an example of a function both on Mathematica and many calculators that has problems near zero, that's computer error, numerical approximation error. Okay, so you gotta be able to do things symbolically as well. All right, we'll see you on Wednesday.